Welcome. This video takes you through the working of a problem that uses a set diagram and then takes the figures from that diagram to use in a decision tree. When we say it's a neat example, we mean that, despite initial appearances, it's actually quite a simple example. Prior to viewing this, it is ideal that you know what a decision tree is, what is meant by expected value, and how to calculate it. However, if you don't, still watch, and that will raise questions you can answer with further research on decision trees. Here is the first part of the problem we're working on. Pause the video to take time to read it. This is where some basic work using set diagrams can be useful. You haven't seen the next part of the problem yet, but you'll find out that we need to know the number of contractors in each section of the Venn diagram. So, to start, we draw the rectangle for the whole set of contractors, and writing 18 above it reminds us of the total number of contractors. Then, for each circle, we'll pencil in the total number of contractors who have that version of WordStuff. So, for example, the total number of contractors in the set who own WordStuff 6 is 7 contractors. 9 of them have WordStuff 7, and 7 contractors have WordStuff 8. Remember, these numbers show the total number of contractors in each set, but we need to find the number for each section of the diagram. Here's why. Again, take time to pause the playback so you can read easily. Now, using the figures provided, let's see what we know. There is one contractor who owns all 3 versions, so they are in the intersection of all 3 sets. No contractor has WordStuff 6 and 7, but not 8. Notice that the words, but not 8, help us clarify precisely where to write 0. One contractor has version 6 and 8, but not 7, so they go here. Now we can work out the number of contractors who only have version 6. There are 7 altogether, but keep in mind that we've already shown 2 of them. Therefore, the number to write in that remaining section is 5. Now for the extra bit, the algebra. We are told that some have versions 7 and 8, but not 6. Since we don't know what the number is, we have to put an unknown there. Let's be daringly original and put an X. Now, in the WordStuff 7 set, we can fill in the missing figure. We have already shown one contractor, so the expression to go in this section has to be 8 minus X. Similarly, in the WordStuff 8 set, our missing number should now be represented with 5 minus X. Remember that we have 18 contractors in total, so all those numbers need to add up to 18. There's our full equation, and the simplification of it. That gives X a value of 2. So now we have the number for each section. Notice too that we have removed the numbers that we penciled in to help with our calculation. Now we're ready for the next part of the problem. Pause the playback to make a note of the figures. Here is where we see more clearly why we had to calculate the number of contractors in each section. Let's look at the contractors who have WordStuff 7 first. While the company is calculating the cost of upgrading these people to version 8, notice that 3 of them will not need to have an upgrade purchased as they already have version 8. Only those 6 need upgrading. Similarly, only 5 of the contractors need upgrading from WordStuff 6 to WordStuff 8, as 2 of them already have version 8. Only 6 contractors need upgrading from WordStuff 7, so here is our calculation. And 5 needed upgrading from WordStuff 6. That's a bit more expensive, and here is our calculation. And the total cost of upgrading everyone is as shown. Now the question becomes whether to pay this money or not. Here are the issues that the RTO has to consider. Pause the playback so you have time to read through carefully. And this is where our decision tree comes into play. Remember, a decision tree gives us a mechanism for giving numerical values to possible outcomes of a decision, and they take into account payoffs, costs, and uncertainties. The square represents a decision node, and since it's the first one, it is also referred to as a root node. One option we have is to choose to pay the $10,800 to upgrade 11 contractors to WordStuff 8. The other option is to not pay for the upgrade, but that introduces some uncertainty about the number who may leave and those who may stay. If they leave, there's the estimated cost. By the way, the triangles indicate end nodes. They show that that is as far as we are extending that branch of the tree. Even if the contractors stay, there's an estimated cost involved with lost productivity. Now remember that the circle represents a chance node. That is, one where there is uncertainty about the outcome. In this case, the best estimates are that there is a 0.5 probability that the contractors will leave and a 0.5 probability that they will stay. The next step is for us to calculate the expected values. The expected value of choosing to pay for the upgrade is straightforward. It's a cost of $10,800. For the chance node, we need to include the probabilities in the calculation. Here is the individual expected value, the EV, if the contractors leave. It's the probability times the costs. And here is the calculation for the branch where the contractors stay. But remember, to make the decision, we need to head to the left of the diagram, back towards the decision node, and get an EV for lines coming from that node. So we need the overall expected value for the chance node. We get that by adding the expected values for the branches coming off that node. Now we have an expected value for each of the nodes coming from the decision node. Which do we choose? We choose the one with either the best payoff or, as in this case, with the least cost. So in all likelihood, after taking qualified cost and uncertainty estimates into account, the RTO will be better off paying for the upgrade. Of course, that leaves aside other issues such as whether providing this upgrade will set a precedent, for example. Say, when WordStuff 9 is released, will all the contractors expect that the RTO will pay for their upgrade? And you thought running a business would be simple.